Hello. Today we will start investigating a new type of differential equation. Namely, it will be systems of differential equations. We can see the formal definition on the slide. We can see a representative example. And what do we see? Well, first of all, we are restricting ourselves to linear differential equations, because for a general case, there isn't really much we could do. Second, we are restricting ourselves to equations with constant coefficients. So we saw such a restriction before. We have it here again. In the general form, again, there is a 1, 1, 2, 1, and so on, without any x in it. Another interesting novelty is that in linear differential equations, when we were looking at them previously, we wanted to see all the unknown functions, or rather the unknown function and its derivatives, on the left. Here, the unknown functions are actually on the right. We can see them over here. We can see them over here, y1 through yn. The functions as such are on the right, and they form a linear combination. That's why it's a linear equation. On the left, we just have the derivatives. And in fact, there is just one. The first derivative of one of the functions. So we are not allowed to put a second derivative here or anything like that. But we are also not allowed to put, let's say, y1 prime plus y2 prime. This is not allowed either. So these are quite restrictive requirements. But still, the situation is not too bad, because in applications, we have exactly this type of equations. Typically, you have some quantities that you want to investigate, and the natural question you ask is, okay, how does this first quantity change? And when you get the answer using physics, biology, whatever background you have there, very often it has exactly this form. This tells you about the change of the first quantity, and this tells you about the change of the second quantity. And if you get lucky, then the change is governed by some linear formula. And you have your nice system of linear differential equations that exactly fits this pattern. You can notice that apart from the linear combination of your y's, there's also some extra part. That's the right-hand side, over here and over here. And typically we call it the right-hand side. We denoted b in our notation. And if these guys are 0, then we say that this system is homogeneous. So there is really nothing new. Now, when we have a system, we are typically asking for a general solution. We expect to find infinitely many of them, if there are any. But sometimes we are interested in a specific process which is governed by the system. Then we are looking for a particular solution. And one way to specify it is initial conditions. So here is an example of initial conditions. How do they look like? Well, I have two unknown functions. And for each unknown function in my system, I also have the first derivative. So this is like a throwback to the beginning of the course when we are dealing with just ordinary differential equations of order 1. And also the form actually fits with what we did at the start. So it's not really surprising that I simply say how y1 and y2 should start at some time 0 or some other suitable time. Okay? So there are two conditions like that. They fit nicely with our settings. And the slide tells us that this is the general case. So if we have an n by n system, n equations, n unknown functions, we also want to see n initial conditions, and we are simply specifying the value for the unknown functions. Very nice. Because it's so nice, we can expect some nice theory. So let me just show the obligatory existence and uniqueness theorem. Here we go. And there is not really anything surprising here. It says that, okay, we should be careful. There is really no trouble from constant coefficients. That's obvious. There is no trouble here, but the right-hand sides that can be restrictive. For instance, if I had 3 divided by x here, I should say, okay, x is not equal to 0. So I should be careful. Depending on the right-hand side bi, that's the start of the second paragraph, I look where the right-hand sides b are continuous, and on such intervals, I have my particular solutions for every initial value problem I want to solve. So whatever I put here for the initial conditions, for the initial values, there should be a solution. So that's the typical existence uniqueness solution. Very nice. The systems are really well behaved, as long as the right-hand sides are nice. But now the question is, where do I get those solutions? So that's the main topic now. And we actually take inspiration from linear algebra. Or rather, I go even back in time. When I encountered my first system of algebraic equations, it was a 2-by-2 system. I think it was like late elementary school, whatever, I don't really remember anymore. And they didn't teach me any theory. They just said, okay, you pick one equation, you express one unknown, put it into the other equation, and it works out. I didn't worry about any theory. I just did it intuitively. And it worked. Let's try it again. Here we go. Okay, which one? This one is shorter, so I sort of like it better. From the first equation, I'm going to express one of the unknowns, and obviously y1 is not a good candidate because y1 appears in two forms. So the only thing I can express is y2. I'm going to isolate it. y2 is y1 derivative minus 2y1 plus 3. So that's my, okay, I guess you could call it elimination formula or reduction formula, whatever. I use it, substitute it into the second equation, and we should get something nice. Let's see. y2 derivative. So I should take derivative of the right-hand side. y1 double prime minus 2y1 prime, and that's it. Derivative of 3 is 0, is equal to y1 plus 2 y2s. So it's double this. I double it, I double it, I double it. Okay. Plus 3x minus 4. Okay. Let's tidy it up. What is it? This is a linear differential equation, just one. So we know how to solve it. And in order to do it efficiently, we need to rearrange it so that it conforms to this form that we had for linear differential equations. So all the y1s, I want to see them on the left. Let's see. y1 second derivative. 2 and 2 is 4, minus 4 y1 derivative. 1 minus 4 is negative 3. I move it here, it becomes plus 3y1. Perhaps I should have, the derivative, second derivative, derivative, no derivative. Okay, let's be organized. Yeah, I think it's okay. So all the y's are accounted for. Now we go on the right-hand side. 3x plus 2. Hopefully that's it. I have a linear differential equation which should be equivalent to the original system. So that's a reduction. When you pull one equation and use it to get a transformation formula, your system decreases by 1. There is one less unknown function, one less equation. So from 2 by 2, I go to 1 by 1. Very nice. Okay, what do we do here? We just solve it. So actually, that's a review of linear differential equations. Let's see. First, I find the homogeneous solution. And to save time and space, I'm going to go directly to lambdas. The characteristic equation, lambda square minus 4 lambda plus 3 is 0. Okay, this is a school problem, so I'm feeling mildly optimistic. Will it go by factoring? And the answer is yes. So lambda is 1 and 3. That's nice. Okay, I will not write the homogeneous solution because I will be writing it later on anyway. So let's do it like that. Part B. The right-hand side. Let's deal with the right-hand side. I need to find a particular solution. I will use the guessing method. It's my favorite. Undetermined coefficients method, officially. So, what form of the solution am I looking for? This is just a polynomial of degree 1. So I think that there should be a solution that looks like this, ax plus b. How about correction? Good question. What is the lambda? No exponential, no sine cosine, so lambda is 0. Do I see 0 here in the homogeneous part? No, I don't. So there is no correction because there is no overlap, no match of lambdas. So that's not just a baseline guess, this is the final guess. That's how it should be. Good. Okay, that's my guess. I put it into my equation and I see what happens. Second derivative is 0, so far so good. Minus 4 first derivatives. Minus 4 and the derivative is a. Plus 3 times my function, 3ax plus 3b. And this should be 3x plus 2. Okay, I look at it and I say, wait, x is over here. This looks really simple. A must be 1. Which is nice. It's an integer, so this looks hopeful. How about the absolute terms? There is 3b here, 2 here, negative for a here. These all are absolute terms. Let's put them together. On the left, actually a is 1. So this is negative 4 plus 3b, and this is supposed to be 2. I move 4 here, 6 divided by 3, b is 2. Okay, so I found my a, I found my b, so I know my particular solution. Again, I'm not going to write it down. I jump directly to the general solution. Okay, y1. Where is y1? Here. y1x. Structural theory says you should put together your particular solution and your homogeneous solution. The particular solution, a is 1, b is 2, x plus 2. The homogeneous solution, I didn't write it, but I see it here virtually, essentially. It's a combination of exponentials with 1 and 3, so it's a e to x plus b e to 3x. Okay, that's my y1. That's a solution, a general solution of this equation, and therefore it also works for my system. But I also need y2, and for that I need this transformation formula. So, y2, let me put it somewhere here. y2 is y1 derivative. y1 is here. I take derivative. 1 plus a e to x plus 3b e to 3x. Okay, minus 2 y1s. So I take this and I subtract it twice. Minus 2x, minus 4, minus 2a e to x, minus 2b e to 3x. And finally, I should add 3. I guess I can do it here, plus 3. So that's my intermediate result. And here I will polish it up. So there will be this particular part, probably, or something similar, which works with x's with polynomials. Do I see something like that? Yes. I see minus 2x and some absolute terms. 1 and 3 is 4, minus 4 is 0. So that part is gone. Great. How about a's and e to x? I can see them here. So it will be minus a e to x. And finally, I can see b's here, and e to 3x is here once. Plus b e to 3x. That's it. I have two functions for my 2 by 2 system. Nice. Do I see any restriction? No problem here, no problem here. X belonging to real numbers. Region of validity, and I am done. I just found a general solution for my system. If you don't trust me, then you can take these two formulas, substitute them for y1, y2 everywhere, and you will check out that left-hand side is equal to right-hand side in both equations. It does work. This should be the solution. Let me see. Yeah, I think so. Nice. So this is really the heart of what we are trying to learn here, how to find a general solution. Once we have it, the rest is simple. So just for the sake of completeness, this was stage 1. Finding a general solution. Now comes stage 2. We work out the initial conditions. How do we do it? Just like before. We know how to do it. These are the requirements, and we have formulas for y1, y2. So we take 0, substitute, and compare with the prescribed outcome. Let's see. 0 into y1. 0 here, 2 here, 0 here, so it's plus a, 0 here, so it's plus b, and this is supposed to be 3. y2, 0 here, 0 here, so it's minus a, 0 here, so it's plus b, and this must be 1. That's the requirement. Okay, what should I do with it? Okay, let's play it simple. I just add the equations. If I add them, I get 2 plus 2b is equal to 4, which means that b must be, let's see, 2 here divide, b must be 1. Easy. And now I take this and substitute into the second equation, and I figure out A. A is 0. That was easy. Okay. I know A, I know B, I have my general solution formula, I know my particular solution. y1x, y2x is x plus 2 or negative 2x. A is 0, so this part is gone, so I'm just adding 1 times the exponential. Plus e to 3x, plus e to 3x, comma, comma, x from the real line. Here I go. So really, the initial conditions, piece of cake, no problem there. Okay, that was the elimination method. Reduction of the size of the system in exchange for increased derivative. Okay? The order that you get at the end directly corresponds to the size of your system. If there were 3 equations, I would do 2 reductions, and the highest derivative would jump to the third one. Okay? Everything seems to work nicely. Let's confirm it officially. Here is a fact. Whenever you get a system of linear differential equations of order 1, and by the way, even if the coefficients are not constant, you can still do this, what you get is one linear differential equation which has order n. Then you can solve it, and after you solve it, using those reduction formulas, you work out the remaining functions for a system. So this looks like a good approach, especially since we have really nice, efficient ways for solving linear differential equations. But actually, this is not something that people would do. 2 reasons. One reason is that it's not really easy to teach computers how to do it. And you may say, okay, who cares about computers? We are humans. I like it. I'm going to do it. Well, there is another problem. And for humans, let me show you another example. Here we are, a 3x3 system, linear equations, constant coefficients, almost homogeneous. I just put +1 here so that we can see that what I'm going to do works also for a non-homogeneous case, but this is not really substantial. 3 equations. I choose one of them. Quite frankly, I don't see any reason to prefer any of them, so let's stick with the first one. From the first equation, I can isolate, well, let's see, y1 is out of the question. 2 different forms. y2, y3, these are the candidates. If I try to isolate y2, I would need to divide by 2, and I will get fractions, 1/2, 1/2, 1/2, which is not a tragedy, but it's inconvenient. You have to write more characters. So let's not waste time. Let's isolate y3. So I'm isolating y3, and I get y1 derivative minus y1 minus 2y2 minus 1. And that's the formula which we previously called star. Let's try it again. That's an important formula. Okay, I take this formula, substitute for y3 into my other 2 equations. From this equation, I get y2 derivative is equal to minus y1 plus 2y2 plus 2y3. So I'm doubling whatever is here on the right. 2y1 prime minus 2y1 minus 4y2 minus 2. So far, so good. And now, with the third equation, I'm again substituting for y3, which also means I'm substituting on the left. So I have to take the formula for y3 and differentiate. And I get y1 second derivative minus y1 derivative minus 2y2 derivative, negative 1 disappears under differentiation, is equal to 2y1 plus y2 plus y3. So I'm adding this formula. y1 prime minus y1 minus 2y2 minus 1. What kind of equations did I get? Let's have a look at them. Let's try to rewrite them so that they have the right form. All the derivatives must be on the left, some linear combination of y1, y2, and so on the right. We will see what happens. Let's start with the derivatives. y2 derivative, I like that. y1 derivative is on the right. I have to move it on the left. Then there will be lots of minuses. Perhaps I will also change the sign. Two operations in one. So I'm moving 2y1 derivative to the left, and then I'm changing sign, and it again is plus 2y1 derivative. y2 derivative stays, and I'm changing signs. Let's hunt for y1. y1 is here. Negative once, negative twice, so it's negative 3 times, and I'm changing sign, so it's 3y1. Let's hunt for y2s. Negative 4 plus 2 is negative 2, and I'm changing signs, plus 2y2. Is there anything else left? Yeah, I'm changing signs, plus 2. That's the first equation. Second equation. All the derivatives on the left, and I guess I will keep the signs. Okay, y1, the second derivative. How about the first derivatives? I'm subtracting and still subtracting another one. So it's minus 2 y1 prime. How about y2 derivative? I can see them only here. Minus 2 y2 derivative is equal to y1s. Let's hunt for them. 2 minus 1 is just 1 y1. y2s are subtracted, and minus 1 at the end. Okay, so what did just happen? From a 3x3 system, we used one reduction formula to pass to a 2x2 system. So far, so good. And that's the end. This is where the good part stops. What would be the next step? I choose one equation, and I use it to express one unknown. I isolate it. From the first equation, I cannot isolate y1 because it's in two different forms. I cannot isolate y2. It's in two different forms. The second equation, the same problem. y1, y2 in two different forms. What do I do? That's a good question. By the way, you may say, okay, I made up an example to be this bad. Perhaps it doesn't happen often. Actually, no. This is essentially a random example. I've just thrown in some 2's so that it's not boring, and it worked out like that. So this is a serious problem. On the other hand, we have a fact here which says it's possible. So how does it fit together? And the answer is yes, it is possible, but one has to use specific tricks. And this is not really good, because what is the main advantage of this type of solution? It's intuitive. You don't need any theory for it, anything bad for it. This just goes by itself, essentially. It's very natural. Once you start introducing some tricks that you have to learn, an algorithm, it stops being nice, and it's not worth actually doing it. So people are not really using this approach when it comes to theory, when it comes to more complicated situations. Elimination is not a viable method. And that's why, as of this moment, I'm banning elimination from this course. I don't want to see it anymore in the lecture, in the classes. I don't want to see it at the exams. Okay? So when I give you a system to solve, definitely use a different approach, not elimination. That said, quite, among us, when somebody gives me a 2x2 system and asks me to solve it, I use elimination because it's convenient. It's nice. But that's not the point of this lecture, of this course. We want to learn something which is viable, which is scalable. That's a good word. Something which is general, a good approach. Unfortunately, this is not it. In fact, things get even more interesting in applications and also in theory. People actually very often go the other direction. They are given a linear differential equation for which we have nice procedures, but instead of working with this equation, they pass to a system. Is that possible? The answer is yes. Let's have a look at a companion theorem. So whenever somebody gives you a linear differential equation of order n, or perhaps a system which need not look like that, just some system where the summation of derivatives is n, you can always change it into n by n system of this proper form. So if you learn how to solve this directly, then it will help us to solve all kinds of other situations. Linear differential equations, but we know how to do them. But it also helps us to solve different systems which do not quite fit into this pattern. They are transferable. This is a very useful procedure, this back transformation from equation to a system. And actually, it's one of possible examples or problems on a test. So let me show you how it works, and you will see that it's a really nice procedure. But we will need some room for that. Here we are, a linear differential equation. Sometimes we get it just by itself. Sometimes we get it with initial conditions. And then it's an initial value problem. Equation of order 3 requires 3 initial conditions. Yes, we have them, so everything fits. You may notice that the coefficients are not constant. So this is a general linear differential equation. It's not homogeneous. The procedure which I'm going to show you is very general, so I could afford to do that. Okay. My aim is to take this single differential equation and transform it into a system of order 1 of the proper form, the one that we have in our definition. Perhaps we should look at it. Just to remind ourselves where we are aiming. The first step is formal. I take y and I call it y1. So this differential equation then becomes y1 third derivative plus sine x y1 second derivative minus x y1 derivative plus e to x y1 is equal to logarithm x. Why did I do it? Well, because now it's a system. It's one by one system. System of one equation with one unknown. Now, of course, I do it this way just because I'm a teacher. I'm explaining it. Normally, I would simply take this equation and I would attach subscript 1 or index 1 next to every y, and I'm done. So this is not a big deal. Now it comes. I have a system, so I'm half the way there. That was my aim, to get a system. But when I compare it with the proper form, there are too many derivatives. So I'm going to reduce derivatives. So in a way, it will be the opposite procedure to what we do with elimination. In elimination, you are reducing the number of equations in exchange for increased derivative. Here, it will be the other way around. I'm going to decrease the derivative in exchange for an equation. But we will see how the equation comes up. In simple terms, I take one derivative of y1, and I hide it from people by giving it a name, y2. That's one of the advantages of mathematics. It's easy to hide things from people. So what happens? This equation now reads y2 second derivative. You can see the reduction, okay? Plus sine of x, y2 first derivative, minus x y2 plus e to x, and I have to keep y1, is equal to logarithm x. So far so good. My equation is still linear, still nice, but now it features two unknown functions, and the degree dropped by 1, which is a good way to go. Let's try it again. I take the derivative of y2 and give it a name, y3. Why not? By the way, before we go on, let's do a little bit of deductive work. What is y2? It's derivative of y1, and y1 is y. So just so that we have the reference to the original equation, this is actually y derivative. y3 is derivative of y2, which is derivative of y. This is actually the second derivative of y, this y3. Okay? This will come handy later on. Let's not worry about it now, but this was the right moment, I think, to think about it. Okay, every derivative of y2 will be replaced by y3. So it's y3 derivative plus sine of x y3 minus xy2 plus e to x y1 is equal to logarithm x. Now my reduction is complete because there is just one derivative. Very nice. Now, where do I get the system? That's a good question. Well, definitely this will be part of it. And there is derivative of y3 in it, So this will be the third equation in my system, and I need to isolate it, because that's what the proper form calls for. y3 derivative is, and let me order it in the proper way. So let's start with y1. I move it to the right, and I start with it. Minus e to x y1. The next guy is y2. I move it to the right-hand side, plus x y2. The next guy is y3. I move it here, minus sine of x y3 plus logarithm. That's the third equation in my system. Where do I get the other equations? The answer is over here. Those substituting formulas, they are in fact equations. This one tells me what's the derivative of y2. The derivative of y2 is, let's see, y3, which is somewhere here. Let me preserve the form. y1 derivative is y2. So it should be somewhere here. And I look at it, and I can see a beautiful 3-by-3 system, which is equivalent to the original equation. If I don't have just equation, but I also have initial conditions for the original equation, I transform them to equations with respect to y1, y2, and y3, and that's exactly where this part comes in. Y at 0 should be 1, y is y1. y1 at 0 should be 1. The derivative is actually y2, so y2 at 0 should be 13, and the second derivative is y3. y3 at 0 should be negative 1. And we get exactly the right type of initial conditions for a system. So as you can see, this process of transforming a differential equation into a system is fairly simple. It's almost automatic, mechanical. So you can teach this to a computer. In fact, you don't have to teach this to a computer. When you compare the system with the original equation, you can see definite similarities. There is a pattern. The equation transforms into the last equation in your system, and then there are those guys that are lying just off the diagonal. See, the diagonal would have y1 and y2. These are just shifted. So if your equation has order 15, then you get a 15-by-15 system where only the last equation will be meaningful. I mean, will be rich. There will be something happening. And all the other equations, they will have just a string of variables off the diagonal. So a computer can jump directly from the equation into the system. It can transform directly the initial conditions. This is very easy for the computer, which brings us back to the fact that these coefficients are not constant. What do? I mean, when the coefficients are not constant, then the whole lambda business is gone. You can use the guessing method either. Well, we would have to use some numerical method. And it turns out that it's actually more practical to take the equation, change it into a system, and apply numerical methods to the system. We will be talking about it later. And then you take your answers and you just throw away y2, y3 because you don't care about them. You just keep y1 because that's y. So from practical point of view, it's actually better to transform into a system. This makes sense. This gives you extra information. This offers you more methods. And perhaps surprisingly, the same thing is sometimes happening in theory. We had existence and uniqueness theorem for linear differential equations. How is this theorem proved? It's actually easier to take your equation, transform it into a system, and then prove existence and uniqueness theorem for systems, and then you take this information and transform it back. So this direction in transformation is practical. The other direction, actually, not so much. Although we have a nice procedure for solving equations like that, well, with constant coefficients. So to make it worthwhile, this transformation in this direction, we definitely need to find a nice procedure for solving systems. That's the main task. And for that, we will actually, again, take inspiration from linear algebra. And for that, we will need a lot of room. Okay. Here we go. In linear algebra, the key to finding efficient methods for solving huge systems of equations, algebraic equations, is to change the notation into matrices and vectors. Let's try it here. In the initial condition, I can see one equation, second equation. They are comparing these equalities, they are comparing numbers. And we know from linear algebra that this can be efficiently written as comparison of vectors. One vector is equal to another vector. The vector on the right has entries 3 and 1. And here there is the number called y1 at 0 and number y2 at 0. So this is not really anything new. What's happening over here? I'm comparing functions. And I can compose functions into vectors. And the comparison then behaves in exactly the same way as before. So I can compare two vectors. This vector has first entry 2y1 plus y2 minus 3, and the second entry is y1 plus 2y2 plus 3x minus 4. And on the left, vector, entries y1 prime, y2 prime. So far, so good. Now, when you have a vector where the entries are functions, then this is in fact so-called vector function. And for vector functions, there is a specific notation, there are some conventions, there are some handy rules. One of them allows us to apply this substitution of 0 not into entries but into the vector function itself. So this is really just a convention how to write things, not an actual recalculation, just a different way of writing this. But of course, it had to be checked that this way of writing makes sense, that it works with formulas, and it does. So at this moment, I'm introducing a vector function which consists of two components, and these are the unknowns. So in fact, I'm asking for this vector function. If I find it, I just look at the components and I have my solutions for my system. Where do I see it here? Well, first of all, I have to take away this extra part, the right-hand sides. They're interfering with my business. So I split it as a summation of two vectors. One of them has entries -3, 3x minus 4, and this is again a vector function because the coordinates or the entries are functions. Over here, I have something interesting. When I ignore this part, I have just linear combinations of y's, and this can be written, and again we recall from linear algebra, as a multiplication of a vector y1, y2, and a matrix which has entries 2, 1, 1, 2. So much for the right-hand side, and we can see that the vector function y1, y2, the unknown function, appeared again. That's nice. How about this left-hand side? Well, I'm going to do a little trick. I will simply take the derivative mark and pull it outside. And I definitely like what I see because, again, there's the unknown function. Now, can I do that? Well, of course I cannot do whatever I feel like, especially because I like it. I have to ask vector function theory whether this is possible and whether it works, and I learned that yes. That's how they define the derivative of a vector function. You just apply it to each entry. And it makes sense in applications. That's important in calculations. So this is proper mathematical step, doing it this way. And now I can see the unknowns always hiding inside this vector. So I can take this vector and call it y vector. It's simply one unknown instead of many, which is nice. Here, this is a matrix. And on the left, I take this unknown vector and I differentiate. And then there's this extra part, and this is a vector. And let's emphasize that it may involve the variable x, while the matrix cannot, because we have constant coefficients. That's an important restriction. How about the initial condition? Well, that's the unknown vector function. I substitute 0, and I get some vector of values. This is some vector y0. And your system, no matter how large, 100 by 100, suddenly looks very nice. This is the beauty of, let's say, convenient notation of mathematics. You take the complications and you hide them from the reader so that the reader does not get too scared. Okay? And the reader gets hooked, and then the reader finds out that it's actually quite complicated, but it's too late. The reader is hooked. Okay, this is a very nice way of writing our problem. Just single equation with single initial condition. Very nice, very compact, very convenient. Let's put it up officially. Now, this is not really anything, deep or surprising. I'm just writing in words this trick. The important thing is that I'm introducing a specific notation so that I can refer to it later. So for instance, the matrix of the system will be called A, always in my theory here. There is the vector of the right-hand side, which is called B, exactly, and so on. The right-hand sides can be 0 if the system is homogeneous. For that, there is a convenient notation. So let me just scroll a little bit. You write 0, but this 0 is a vector, so it has to be written as a vector consisting of zeros. Nothing surprising really here. I look at it, and that's an equation which is linear, but we cannot use directly tools from linear algebra because there's also this derivative, which linear algebra does not feature. It works with numbers, not with functions. But we can take inspiration from linear algebra and from what we did with linear differential equations, because this will be the same. I promised that all equations of any type, as long as they are linear, behave in the same way. And perhaps you were not quite sure how I meant it. Well, let's put my words into a test. This is a linear object, this equation, a linear type of equation. So let's see what we can learn about it. Step number 1, structural theorem. Let's see. We have an equation which is actually a system, masked system, and we find some particular solution on some interval I. Are we surprised? Not really, because we've seen this theorem before. Let's see. Some y naught is another solution if and only if it comes in a special way. Well, we have seen this before as well. And then there's this last paragraph which sort of sums it up and tells us how the structure looks like when you think of all solutions at once. So you take a general solution of the associated homogeneous system, you shift it by your particular solution, and you get a general solution of the original system with right-hand side. So this is exactly like it was for linear differential equation of order n. And the proof, and you will see it now, will be also the same. The only difference is notation language. So let's recall how this thing works. Proof. By the way, that's another of those things which I can ask about at the exam. So yeah, this is an interesting moment. Let's see. There is universal assumption that you have some function yp, but now it's a vector function. So there are several functions as entries. And this guy solves the equation y derivative is ay plus b. And let's call it star. There are two statements, in fact, and I explained it before, so let me just go through it briefly. If and only if means it's an equivalence. Let me start with the direction that goes backwards. And it tells me, if you create a new function, y naught, using the formula, then reading backwards, this y naught must be a solution. So here is my claim. I take yh, which solves the associated homogeneous equation, then y naught, which is obtained by a shift of yh, solves equation star. How can I tell? How do I prove this claim? I simply take my function y naught, substitute into the equation, and I see whether it works. Well, let's have a look at the left-hand side. The left-hand side is y naught derivative. What is y naught? Well, it's yp plus yh derivative. Now, these are vector functions. We know that the derivative is linear when we apply it to functions, and it's also linear when we apply it to vectors of functions. So I can split it. Yp derivative plus yh derivative. Let's see. What's my assumptions? Yp solves the original equation, so when I differentiate it here, I should get the right-hand side. Ayp plus b. Yh solves the homogeneous equation, so yh derivative should be a yh. Now I'm going to factor out a, let's see, I guess over here, yp plus yh plus b, and this is in fact a y naught plus b, which is the right-hand side of equation star. So when I look at this expression and this expression, I can see that y naught solves the original system, and I'm happy. Wonderful. I just proved that the formula yp plus yh generates solutions. Now let's see the other direction. This other direction, as I explained before, shows that this solution machine, solution-producing machine, is exhaustive, that it can reach any solution that's out there. So if we create solutions in this way, we are not leaving any solution out. We are capturing them all, which is important. That's why it creates a general solution. So how does it go? We are going left to right. Somebody gives me another solution. Y naught is a solution, so it solves the equation star. Let's see. What's my task? Or what's my target? Well, I have to show that this y naught came in the very special way. I have to think about it, I have to show that there is yh that works exactly like that. So I have to find this yh. I have to take yh to be, let's say, okay, I see what it's supposed to satisfy, so that's an inspiration. Y naught minus yp. I talked about it when we did this proof for linear equations, so hopefully I don't have to explain that much. This is my candidate for yh. Does it work the way I want it to work? Well, this yh should do two jobs for me. The first job is that when I put together yp and yh, it should provide me with this y naught. Well, let's see. Yp plus yh is nothing else but yp plus y naught minus yp, which is y naught. Check. The first job is done. And of course, I expected that. If this didn't work out, then I must have made some really bad mistake over here. So this is okay. This is to be expected. The interesting part is that this yh should solve the homogeneous equation star, the homogeneous version of equation star. So how do I check? Well, let me again substitute. I look at the left-hand side, which is the derivative of yh. I substitute for yh, and I get y naught minus yp derivative, and again, linearity, y naught derivative minus yp derivative. Now, y naught is a solution of the original equation. So y naught derivative is a y naught plus b, and yp derivative, for the same reason, is a yp plus b. I look at it and I say, okay, that's nice. B cancels. And from these two terms, I can factor out a. A y naught minus yp, and this is actually a yh, which is the right-hand side of the homogeneous equation. So that's exactly what I wanted to see. And my job is finished. I just proved this structural theorem. And as you can see, the structure is exactly the same as before for linear equations, but it's actually more convenient because when we did the proof before, I had to, here, when I was substituting into the left-hand side, I had to put the summation of all the derivatives, and the highest derivative was separate, and so on. It was really, really long. The same ideas, the same calculations, but long formulas. And I tried to shorten it up by introducing a linear operator, and then it hid the complications from us in the best tradition of mathematics. And it worked. Here, there is no reason to introduce some operator L because the equation itself is very convenient. It's very compact. Again, all the complications are hiding inside the notation. So this is a very nice compact proof. And we have the structural theorem. Just out of curiosity, this example, we found the solution using elimination. Let's have a look at it. Let me put it here. y1 was x plus 2 plus a e to x plus b e to 3x. And y2 was negative 2x plus a e, no, minus a e to x plus b e to 3x. Yeah, I think so. The miracle of short-term memory. Don't ask me half an hour from now. Okay. That's the solution when I see it in the original form. When I rewrite it in the vector form, it becomes different. It looks like that. This will be the first coordinate. This will be the second coordinate. Let me rewrite it again. y1, y2 is, and now I will keep this part separate because there are no a's or b's, no parameters, no coefficients. And this part, I'm going to take away a from the first column and b from the second column. Now here I have some coefficients a and b, so I strongly suspect that this will be the homogeneous solution. And then, logically, this should be the particular solution. Is that true? Well, we can easily check. We simply take y1 to be x plus 2, y2 to be negative 2x. We substitute into this system, and we see that it checks out. So indeed, when we take our solution and write it in the vector form, we can identify the particular solution of the matrix form, of this form of our equation. How about this part? Well, again, you can take these formulas, just the a and b parts. This one you call y1, this one you call y2. You substitute into your system, and you see you get a solution, assuming that you ignore this part. You want a homogeneous system, okay? So substitute into this one. Perhaps let me put it over here. y1 prime, y2 prime is 2y1 plus y2, y1 plus 2y2. Is that right? Yes. Okay, so when you take these two formulas and substitute into the system, into a homogeneous system, you will see that they work out. So indeed, that's the homogeneous part. But notice I split it like that. And this reminds me of basis of a fundamental system, of a linear combination of a fundamental system. So this would suggest that these individual vectors are actually also solutions of the homogeneous version of my system. And again, I can check. I can take e to x for y1. y2 could be negative e to x. And I substitute into the homogeneous system, and it does work. So this vector solves the homogeneous system. This vector solves the homogeneous system. This tells me that the homogeneous solutions actually form a space of dimension 2. And again, that's familiar. I have a 2 by 2 system. And the solutions of the homogeneous version, they form a space of dimension 2. This seems to work nicely, the general theory, the structural theory, and our particular example that we solved by elimination. But of course, what we want to do is to figure out how to solve it directly, how to get the vector form of the answer, and then transform it, write it like that. So we will be going the opposite direction, from here to here. But this will not come in this lecture. Today we are interested in structural theory. And here we have a strong reminder of another structural theorem. And you will not be surprised. Here it comes. So we have a system which is homogeneous. And then the solutions on a specific interval form a linear space of dimension n. That's exactly it. The dimension of the space agrees with the dimension of the system. Again, the proof is a carbon copy of what we did before. So let me just do it again, essentially, because it will be on the test, so it's fair to show you, but also I'm going to point out some differences. I will try some slightly different tricks. Let's see. Here we go. So we have some interval. and we are interested on solutions on this interval. Actually, when we look at the system, there is no right-hand side, just the matrix A, and it has constant coefficients. So the solutions exist on the whole real line. So I could be talking about solutions on R, but sometimes we have to restrict ourselves because we are then adding YH to YP and so on. So let's do it in general. I is some interval, and I'm interested in solutions of the associated homogeneous equation, but not associated, in fact. A specific homogeneous equation on this interval I. Okay, that's a set of vector functions, and we are supposed to prove that it's a linear space of dimension n. So that's actually two things. It's a linear space, and it has the right dimension. The proof of the dimension part, I did it for linear differential equations, and the proof wasn't exactly very deep or educational, that's a good word. It wasn't a proof that would teach us something about mathematics. It was based on a very specific trick. So I don't think there is much sense in just repeating the same trick here in a slightly different setting. So let's forget about the dimension. The linear space part, that's actually useful because it shows nicely this tie on linear algebra. So instead of proving directly that this is a linear space, again, we will show that this M is actually a subspace. Subspace of what? Well, we have many candidates. For instance, we can take the space of all vector functions on interval I. This could work. Or perhaps we could be more picky and we could just be looking at functions which are differentiable because we need differentiable functions. So functions that have first derivative that is continuous on the interval I, but these will be vector functions. These are specific notations. We do not really have to worry much because linear algebra allows us not to worry about the overspace, but to simply ask whether this set M is closed under operations. That's how we proved it for linear differential equations of higher order. That's how we will prove it over here. So what are we supposed to do? We should show that this set M is closed under addition and scalar multiplication. And there are two ways in which it can be done. Sometimes people do each operation separately, and that's what I did for linear differential equations. Or people do it all in one calculation. So I will do it here, and you can see both approaches. So I need to do the following. I take two objects, y1, y2, from the set M. I take a scalar, which in our case will be a real number, but it could be complex also in some settings. And we want to show that cy1 plus y2 belongs to M. So this is the formal statement from linear algebra. You start with two objects, a constant, you combine them together, and you want to stay within your set. So this connects together addition and scalar multiplication into one formula, and does the two steps in one go. Now, in order to do that, I have to translate this formal statement into real meanings. y1, y2 come from the set M, so it means that y1, y2 solve my equation, which I'm going to call star. On interval I. Then I have a number, and I'm asking, is it true that cy1 plus y2 solves equation star on I? That's a good question. Well, we simply substitute into the equation. We start with the left-hand side. So let's check. The left-hand side is the derivative of our vector cy1 plus y2, derivative. Linearity, cy1 prime plus y2 prime. Now let's see what are the assumptions. y1, y2 solve our homogeneous system. So it will be c times a y1 plus A y2. Okay, now C is a constant, and this is a matrix multiplication essentially. According to the rules, C can be moved inside, and then we can factor out A. So A is factored out, C moved inside, and I look at it and I say, wow, that's exactly what I wanted. That's the right-hand side of my system. If I substitute in cy1 plus y2. And again, that's the end of the proof. Very nice. So now we can trust also this structural theorem because we saw the proof, well, apart from the dimension. And we are ready to use it. So that's all for today. We learned structural theory for the systems. We saw elimination, which turned out to be a blind alley, but we learned it was an inspiration for this important thing about transforming linear equations into systems. So this will come handy. We are ready. Next time we will learn how to actually find those solutions that we are talking about here. See you then. So I am going to erase this part, this part, this part, this part. Okay, I think I'm doing well. When I get tired, I talk too much, which is not good. And I'm making stupid mistakes. Okay, that's life.